session of today's that is fifth day Atal online FDP program. The today's session 2 speaker is Dr. V. Satish Kumar, our coordinator. I'm happy to introduce Dr. V. Satish Kumar. Dr. V. Satish Kumar is working as an assistant professor, senior grade in the Department of Electronics Engineering, MIT campus, Anna University, Chennai, Tamil Nadu, India, since 2014. He is also acting as a Deputy Director, Planning and Development, Anna University. He has about 11 years of teaching experience in Anna University and Anna University affiliated engineering colleges. He received his Doctor of Philosophy from Department of Engineering Design, IIT Madras, Tamil Nadu, India, 2014. His research interest includes artificial intelligence systems, embedded systems, optoelectronics, machine learning, computer vision, laser remote sensing, and laser spectroscopy. He has published 84 international research publications, which includes 23 number of journals, 7 book chapters, and 54 conferences. He has also have 2 patents in his credit. The publications involve reputed journals with high impact factor like Engineering Applications of Artificial Intelligence, Expert Systems with Applications, Ecological Informatics, Journal of Applied Spectroscopy, Journal of Optics and Laser Technology, IET Image Processing, IEEE Transactions on Dielectrics and Electrical Insulation, Journal of Intelligent and Fuzzy Systems, Journal of Physics D, Applied Physics A, Journal Technology, etc. Presented the research finding in the international forums organized in different countries such as Mexico, Italy, France, and Japan. He has completed successfully 2 projects sanctioned by Science and Engineering Research Board, CERB, funding amount of 48,79,000, and a Center for Technology Development and Transfer project funding amount of 50,000, Anna University. He is one of the principal investigator in UGC sanction project for university with potential for excellence, that is UPE, in biomedical engineering and instrumentation for a seed value of rupees 23 crore. Currently, he is working in 2 projects under TANI scheme. First project titled Design and Development of Internet of Things Enabled Soil Nutrient Measurement System for an amount of rupees 2.27 crore. Second project titled Development of Semi and Fully Automated Intelligent Exoskeletal and Prosthetics for Disabled Communities for an amount of rupees 17.82 crores. He is also awarded with Erasmus grants for staff from Indian universities to make mobility at Universidad Politécnica de Madrid, Spain, between 26/2022 to 24/6/2022. He is also awarded with TNSCSD Young Scientist Fellowship for the year 2019 and 2020 to carry out research activity at IIT Indore for a period of 2 months between 1/1/2022 and 28/2/2022. He is also awarded with Kyushu University Friendship Scholarship to pursue research work for 6 months between August 2012 and January 2013 at Graduate School and Faculty of Information Science and Electrical Engineering, Kyushu University, Japan. He is also a senior member of IEEE, Indian Laser Association, ILA, and Indian Unit for Patent Recognition and Artificial Intelligence, IUPRAI. So he has many things in his credit. We are very happy to have you here, sir. So now I invite Dr. V. Satish Kumar, sir, to deliver a talk. Over to you, sir. Sir, am I audible?
Yes, ma'am. Yes, ma'am.
Yes.
Is my screen visible, ma'am?
Sir, it is loading. Yes, sir. Now it is visible.
Okay, ma'am. Thank you. A very good evening to all the participants of this Atal FDP on next generation algorithms and technological advances. So today I'm going to talk about an interesting topic, which is your vision transformer. How this vision transformer can be used for computer vision applications. So we know that computer vision applications involve image classification, object detection, semantic segmentation, etc. So image classification, which means when we have some information on an image, based upon the information, we can able to classify it, or we can put a label for that particular image. In case of object detection, we can identify the objects in a video frame or in an image. So semantic segmentation, something like I can identify a particular object. I can retrieve such objects from an image. So these applications, usually we will try to do it with the help of a convolutional neural networks. So convolutional neural networks are very popular to do such tasks. So for example, if I take an image, so this image is made up of pixels. And this pixels can be a color pixel or it can be a grayscale pixel. So when we give this image to a convolution layer, so this convolution layer is going to extract the features from the input image. After extracting the features, I need to reduce the dimension of the features. So if we have more features, then the model is going to take a huge amount of time. So in order to reduce the computation time, what we do is we need to reduce the dimension of the features. So that is done with the help of a pooling layer. So pooling layer is used to reduce the dimension of the feature maps. If I want, I can again use another convolution layer where I extract much more higher level features. And then again that features can be reduced in size using again another pooling layer, and we can have as many number of convolution layers and pooling layers together. So finally we have the features which goes into a neural network. So and the neural network is going to make a prediction in case of a image classification pattern. So that is how a conventional convolutional neural network is going to work for a image application or image classification. So today I'm going to talk about a vision transformer which provides an alternative to this convolutional neural network, So there are a lot of convolutional neural network models are available like ResNet, VGG, YOLO architectures, DenseNet architectures, etc. So all these architectures performance can be better with the help of a vision transformer. So here I'm going to talk about how this vision transformers are going to be used in case of a image classification task. So this transformer, it provides at least 4 times the computation efficiency, 4 times the better performance or accuracy when compared to the conventional CNN models. So you might be knowing about ChatGPT AI, where it makes use of this transformer architecture. GPT stands for Generative Pre-trained Transformer Architecture. So here the important aspect behind this transformer architecture is attention mechanism, where we have to give our attention in the input data. Which part or which text is going to be given with a higher attention so that the generation or prediction is going to be much better. So that is what makes this ChatGPT to be an interesting one. Now let us look at a vision transformer. First, I will talk about the overall picture of the vision transformer. So here you can see that we take an image. This on left side bottom, you can see an image, and this image is divided into small patches. This image is divided into small patches. Here, for example, I have taken 9 patches. So this 9 patches, each patch is being converted into a vector. Each patch is converted into a vector. And for each vector, we put the positional information. This numbers 0, 1, 2, 3, 4, 5, 6. It indicates the position of our data. Then this data goes into a transformer encoder. And after transformer encoder, it goes into a multi-layer perceptron where our prediction is going to happen or classification is going to happen. So here I talk about a very abstract version of the vision transformer. Now let us look at what is there inside this transformer encoder. Okay, so here on right side, we show this transformer encoder where the input is the embedded patches. The embedded patches are nothing but the patches from the input data. And these patches are being converted into a vector. And this vector is normalized. Then after normalization, it goes into the multi-head attention block. After multi-head attention block, again normalization happens. After normalization, multi-layer perceptron is going to make a prediction. I will talk about each and every block. What each block is going to do, what operation each block is going to perform, I am going to detail it in the subsequent slides. So this is an overall picture I am trying to say here. So here what we do is we take an image, we divide that image or segment the image into small patches. Each patch I'm going to convert it into a vector. And for each vector, we are going to put the position encodings to that each vector. Then it is given as an input to a transformer encoder. So the transformer encoder, it does this operation on which is specified on the right side, like normalization, multi-head attention, normalization, and then we have a multi-layer perceptron, which is going to give that classification part. So with this small introduction, we will go into detail of how this transformers are going to work. What happens inside this each block, like multi-head attention means what? How multi-head attention occurs. So such aspects we are going to discuss in detail. Let us take a simple example. Okay, I'm going to talk about a transformer first. Then later on, we will go with the vision transformer. So a transformer, it is mainly used in your machine translation application. Like if I have some sentence in some language, if I want to convert that sentence into some other language without changing in the meaning, that can be done with the help of this transformers. So I can take a sentence in one language and I can output it in the another language. So for example, here we have a French statement, Je suis student. This statement is given as an input to this transformer. And this transformer, what it does, it finds the equivalent English version of this statement, which is I am a student. So this transformer, what is there inside this transformer? Right on bottom, I show this diagram. So in this transformer, we have an encoder and a decoder. So the input to the encoder is the French statement and the output of the decoder will be an English statement. Right. So now when I look at it in detail, what happens in this encoding part and decoding part, which is shown on the right side. So here what we do, we take the input and this input is something like a text. So this text, first it should be converted into a vector, a numbers or array. This text should be converted into a vector. So that is done with the help of an input embedding mechanism. Using input embedding mechanism, the input statement gets converted into a vector. Then after converting into a vector, we try to provide the positional information. Here I have three words. What is the position of each word that is being added here? That is positional encoding. After adding it into the positional encoding, we give it to the encoder block. So this is your encoder block, which has a multi-head attention module. Then there is a feed-forward neural network. In encoder, we have two major blocks. One is multi-head attention module. Another one is a feed-forward neural network. So in this multi-head attention module, what it does is it finds the attention mechanism. If I have a statement with some n number of words, how one word is related to another word, or how if I have one word, how much value it will be added when I put some other word in the sentence. So that attention mechanism can be identified. That is multi-head attention. So after finding that attention mechanism, we give it to a feed-forward network, and then the output of this encoder block, it goes into the decoder. On the decoding side, you see that we try to generate the sentence in a sequential manner. So we give the inputs one by one. We get the outputs which are generated in a sequential fashion, which will go as an input here. And again, the information from the encoder will be utilized in the decoder block to generate the subsequent words. That is what happens in your decoder side. Anyway, we will try to discuss everything in detail. So now let us look at it in much more detail. So I'm going into the architecture part. So earlier I showed that we take a statement in French. It is given to an encoder. Then the output of the encoder goes to a decoder, and the decoder is going to generate a statement in English. Now, instead of a single encoder, I can have a stack of encoders. Same way, instead of a single decoder, I can have a stack of decoders inside the transformer architecture. That is what I show here. So it's the same diagram, but what we have done is a single decoder is replaced by a stack of encoders. Same way, a single decoder is replaced by a stack of decoders. So we give the French statement to the bottom encoder. So this bottom encoder generates an output. That output goes as an input to the upper layer encoder. And that upper layer encoder, again, it generates an output. It goes to the subsequent encoder. Like that, it propagates. And the topmost encoder, it generates an output. This output is given to all the decoders. So since I have a 6 encoder here, we will try to match the number of decoders also. 6 encoders will be matched with 6 decoders. So all these decoders will get the information from the topmost encoder, and based upon that, the sentence will be generated. Now let us go one step further. What happens inside this encoder and what happens inside this decoder? So if I take an encoder, what is the fundamental blocks in the encoder? It is going to have two basic blocks. One is called a self-attention block. Another one is called as a feed-forward neural network block. So these two blocks will be available in the encoder. In all these encoders. So here I have 6 encoders, which means bottom encoder will have a self-attention block, then feed-forward neural network. The same way, the other encoders are also going to have the self-attention block and feed-forward neural networks. So this self-attention block, what it is going to do? It helps the encoder in finding the relationship between the sentences, or how one word is related to other word, whether the subsequent words will have some useful meaning added to this current word or not. So such information will be included in the self-attention block. And then it goes into the feed-forward neural network to generate a vector. Now, with this introduction, we go again into the self-attention block. What happens inside the self-attention block, we try to see. So here we show a similar architecture, an encoder and a decoder. So in an encoder, as I said, we have two blocks, self-attention block, and there is a feed-forward block. In the decoder side also, we have the same blocks, self-attention and feed-forward block. In addition to these two blocks, there is a sandwiched block in between, which is encoder-decoder attention block. So from this encoder, we get the important information. That information is being fed to the decoder as a data. Yeah. So that is the difference between an encoder and a decoder. So in a encoder, we have only self-attention and feed-forward blocks, whereas in a decoder, we have one more block which is called as encoder-decoder attention block. Okay. Now let us start with the actual operation, how a transformer is going to work. So as I said, we are going to take a French statement, Jesus udent. So this is a text information. So in order for this text to be given as an input to the network, what we do, we convert it into a vector. How to convert it into a vector? Using embeddings. So for example, if I have something like hello world. Okay, let us take this is a statement, hello world. Right? So I want to convert this hello into a vector, same way world into a vector. In our dictionary, we might have some 10,000 words or 10,000 words or 20,000 words, depending upon the size of your memory. You can have the number of words in your dictionary. Then we can use a dimension of a vector for representing each of these words. For example, I can use some 10 elements to represent the word called as hello. So in a vector, I'm going to have 10 elements. So this is called as a 10-dimension vector. Okay, it need not be 10 elements. It can be 20 elements. It can be 100 elements, depending upon what type of computation power you have. So here for simplicity, for explanation purpose, I'm trying to say that my word is encoded as a 10-dimension vector. So the hello will be represented as a 10-dimension vector. Same way, world can also be represented as a 10-dimension vector. Instead of 10-dimension, I can use a 100-dimension vector. 100-dimension vector in the sense 100 elements will be there in a vector. In that case, hello will be represented by 100 elements in a vector. Same way, world will be represented by 100 elements in a vector. So that is what we call it as embedding, to convert your text into a vector form. So here we are taking a French words. So this French words gets converted into a vectors called as x1, x2, x3. So let us assume the dimension of this vector is 512. So 512 elements are there in this vector. So for example, if I take a vector 10, 20. If this is a vector, it is called as 2-dimension. Okay, 2-dimension in the sense 2 elements are there in this vector. But here I'm talking about 512-dimension vector. Right? So this x1 is going to have 512 elements. X2 is going to have 512 elements. Similarly, x3 is also going to have 512 elements. So this process of converting text into a vector is called as embedding. It is called as embedding. So the first step is to convert the text into a vector. So we get this x1, x2, x3. Since I have 3 words, I get 3 vectors, x1, x2, x3. If my sentence has some 10 words, then I will get 10 vectors. If the sentence has some 100 words, then I will get 100 vectors. So depending upon my length of the sentence, I'm going to have the vector number of vectors. So if I have, for example, in our data set, if I have something like one sentence is 10 words, another sentence is some 20 words, another sentence is 5 words, another sentence is some 50 words. So like this, variable length sentences are there in our data set. Let us assume. In that case, in order to have a common vector format, we can choose the sentence which has the longer sequence. So here 50 words are there. So I can use something like a 512 dimension vector. for each words. For each words, I can specify. So the important thing which I want to tell you here is, even though I have a variable length sentence, the vector size, I'm going to have it as a constant value. I should not have something like a 10 word sentence, 10 dimension. For 20 words sentence, 20 dimension, right? So we should represent all the sentence as a common dimension. Then the processing or calculation will be much more easier.
Sir, I have a doubt, sir, basic doubt.
Hello?
Hello.
Yeah, please.
There are some concepts called attention, right? You told about self-attention. What
Yeah,
is the importance or significance of an attention block, or
yeah,
what is
yeah.
the use of it?
I will come to that, ma'am. I will explain the process, what happens inside the self-attention block. So I will try to just explain it.
Okay, sir.
Please wait, ma'am. Any other queries? Okay, so the first step which we are going to do is, we are going to convert your text into a vector. Next, now this process is done, right? So we have completed this process. We have taken a text, converted into a vector. Now this vector is going to go into a self-attention block. Now we will see what is happening inside this self-attention block. Once it goes into the self-attention block, it is going to generate another vector called as Z1, Z2, Z3, depending upon how many words I'm going to have. Okay, here I have 3 words. So I have 3 outputs from the self-attention block. Then this 3 outputs goes as an input to the feed-forward network, and thereby again I will get 3 vectors from the feed-forward network. We will look at one by one what happens inside each block. So let us take again the same example. The encoder, as I said, we can have a stack of encoders, right? So here we talk about 8 encoders. So for the bottom encoder, we will take the inputs as a text, and then it is getting converted into a vector. It goes into a self-attention block, and then it produces an output. This output goes as an input to the feed-forward network, and the feed-forward network is going to produce again a vector output. Whereas in case of a second encoder, okay, so the input to the second encoder is the output from the first encoder. So the output from the first encoder is this R1 and R2. It goes as an input to the second encoder. Same way, the output of your second encoder will be given as an input to the third encoder, right? So what I'm trying to say here is that embedding is applicable only to the bottom encoder. For the bottom encoder alone, I need to convert this text into a vector. For all the upper encoders, already the input is in terms of a vector. So I can give directly to the particular encoder. Now let us take a simple example, a statement. The animal did not cross the street because it was too tired. This is the statement which we are going to give it to the transformer architecture. So here if you see, this is one word, second word, third word, fourth word, fifth word, sixth word, seventh word, eighth word, ninth word, 10th word, 11th word. So there are 11 words in this sentence. Now, when I want to have an attention mechanism, right? So for example, once again, I will repeat the sentence. The animal did not cross the street because it was too tired. So if our word is it, let us assume if our word is it, what it represents. This it means what it refers to, whether it refers to an animal, or it refers to a street, or it refers to a tire. Right? It, whether it is referring to the animal, right? So whether animal is tired, or the street is tired, or is tired, right? So when I take a word, where this word as its reliance or where it has its attention, right? That is what we are going to find in our self-attention block, right? In a self-attention block, we want to see how one word is related to another word, or how one word is going to influence another word, right? So that is what we are going to see in the self-attention block. Again, we put it in a diagrammatic way. When I talk about it, where its attention is. If you see here, one such attention says this it is referring to the animal, right? So the thicker line means more attention. Thinner line means less attention, right? You can see the thicker line is with the animal, and also you can see tired, too tired also has some thicker lines, right? So now this word gets attention based upon the words like the animal tired. This is one mechanism. If I use another attention mechanism, then in that case, this it might be related to street also, right? But we need to find which words are more apt or more attentive words to the word which we are talking about. That is what we are going to find. So now let us go to the mathematics part, right? I took this sentence, thinking machine. Each word gets converted into a vector, right? So this is a 512 dimension vector. X1 is a 512 dimension. Same way X2 is a 512 dimension vector. So this process is called as embedding process, right? So till this we have seen. Now what I'm going to do is I'm going to take three matrices WQ, WK, and WV. Q stands for query, K stands for key, V stands for value, right? So we are going to take three matrices. One is query matrix, key matrix, and value matrix, right? So we are going to take three matrices. So what is the size of this three matrix? I'm going to take something like 512 by 64 is the size of my matrix, right? Here, what is the size? The input size is 1 by 512. One row, 512 elements. So here also X2 is one row, 512 elements. So now I'm going to take three matrix, query matrix, key matrix, and value matrix. So the dimension of this matrix is 512 by 64. I will come to this why this is 512 by 64. So 512 rows I'm going to have, and in each row I'm going to have a 64 elements. So when I take this three matrix, I'm going to multiply this three matrix with this input vector X1 and X2. When I do that, I will get query matrix Q1, Q2, key matrix K1, K2, value matrix V1, V2. So what will be the size of this query, key, and value? It will be 1 by 64, right? Because my input is 1 by 512 matrix multiplication with 512 by 64. If I do that, what will happen? My output will be 1 by 64. So we generate three such matrices. One is query matrix, key matrix, and value matrix. What is the dimension? It is 1 by 64 for Q1, Q2, K1, K2, V1, V2. I will say why this is required. So far, any doubts? Okay, so using this three matrix only, we are going to find the attention mechanism. How this word X1 is related to X2 or not. If I have multiple words, how one word is related to another words or not. that is identified with the help of this three matrices: query, key, and value matrix. Now you can ask me a question. What should be the values for this WQ, WK, WV? Right? So this X1 and X2 comes from the embedding layer, right? But how to define this WQ, WK, WV, right? Initially, we don't know, right? So what we do, we try to assign this matrix in a random fashion, right? So we try to assign this matrix in a random fashion. So after random assignment, we do this multiplication, multiply of X1 with WQ. I will get Q1. If I take X2 into WQ, I will get Q2. Same way, X1 into WK, I will get K1. X2 into WK, I will get K2. Same way, V1 and V2 can be obtained. So now we have computed Q1, K1, V1. Same way for the second word, Q2, K2, V2. All right. So now what we are going to do, we are going to do a dot product of Q1 dot K1. Right. So Q1 dot K1 we are going to do. Same way Q1 dot K2 also I am going to perform. Right. So why we are trying to do this is how one word is related to another word that we try to find. Right. So we try to see whether my Q1 is related to K1 or it is related to K2. That is what we are trying to find here. So relationship between the subsequent words we are trying to find here. So when I do this, I get some value. Okay, Q1 dot K1 equal to 112. Same way Q1 dot K2, I get some 96. Same way what I can do for the second word, I can do something like Q2 dot K1 is one value. Another one is Q2 dot K2. I can find. So how the second word is related to the first word I'm trying to find. So Q2 dot K1 is how second word is related to first word and how the second word is related to the second word itself. That also I'm trying to find. So like this, I need to compute this value. So this value we call it as a score. Right? So score. So this score gives how one word is related to another word. So usually the word will have higher relation with the same word, whereas the word will have a lesser relationship with the subsequent words. So this Q1.K1 or Q2.K2 will have a higher value when compared to the subsequent values. So thereby we try to compute this score. Once I compute this score, what we do is next step is I'm going to take. So we have computed this till now. What we are going to do is we are going to take the root of we are going to divide this number score by a factor of 8. Why 8? Because I have used a 64 dimension values for query, key, and values. So thereby we try to take the root of this dk. So root of dk is nothing but 8. So root of 64, which is nothing but 8. So we are going to divide this value by 8. We get this 14 and 12. Now this value, I am going to send it to a softmax activation function. Softmax activation function. So the softmax activation function you might be knowing e power z divided by summation of I equal to 1 to k e power I. Okay, so I can put something like e power I here. Okay, this is a softmax activation function. So a softmax activation function will try to provide the value in terms of a probability score. It will try to provide in terms of a probability score. So what we do here? So here we take 14. So e power 14 divided by e power 14 plus e power 12. Right? So this is a softmax activation function. So when I do this, I will get this 0.88. Same way, I can compute e power 12 divided by e power 14 plus e power 12. So if I do this, I will get this 0.2. So what we are trying to do is we are trying to make this value to come to a probability score, right? So probability score of 100%. In 100%, how much this first word is going to contribute, how much the second word is going to contribute. If you see that 88%, the first word is going to contribute, 12%, the second word is going to contribute. Right? So that is what we try to find with the help of a softmax activation function. Right? So we are doing some mathematical steps, right? So why we are doing this, I will try to explain a little bit later. So we are doing the steps. We take the sentence, convert into words, convert the words into a vector. With the help of a vector, we try to find query, key, and values. And we try to do a dot product of q1.k1 and q1.k2. Same way for second word, we do q2.k1 and q2.k2. And then we try to divide it by 8. And then we apply it to a softmax activation function to get the probability scores. So the same operation we have described in terms of a block diagram here. So we take a query matrix, key matrix, and value matrix. So first query matrix and key matrix, we do matrix multiplication, which is the dot product. That is this one. Then we do scaling. Scaling in the sense we are going to divide it by 8. This is the second operation. After this mask right now we are not going to use. Directly we are going to give this value to a softmax activation function. So you will get this value. Then this softmax, next step. After getting this softmax activation function, I'm going to multiply this softmax value with the value parameter. So that is what we are going to do next. Right? So we have completed till this. So after softmax, what we need to do? We have to multiply this softmax output with V. Right? So we need to multiply it with V. So we take this V values, multiply it with the softmax value, then add this vectors to get the Z1. Same way when I do it for the second word, so you will get something like Q2 K1, then Q2 K2. Then when you divide it by 8, you will get some numbers. Then by applying a softmax activation function, you will get again some numbers. Then you multiply the softmax with this V1 and V2 to get the Z2, right? So you will generate this Z2, right? So what happens here? I take an encoder. We give two vectors, X1, X2. So it passes on to this encoder. What is the output of this encoder? After self-attention block, we get Z1 and Z2 as an output. Right? So this is after self-attention block. So why this is called a self-attention block? Because here what we do, we try to find how one word is related to the subsequent word. Okay. So for example, after this softmax, I have something like vector 0.5, 0.25, 0.15, 0.10, right? So this is one word. This is the subsequent words relation with this first word. Then I can say that since this value is high, so this word is providing some information to this first word. That is why we try to do this operation. Whereas this fourth word, it has very little value to this first word. By finding the softmax function, we can able to see how one word is related to another word. In another case, it can be something like this. I can have the first one can be 0.5, second one is 0.1, third one can be something like 0.3, next one is 0.1. Here what happens? The first word attention is available in the third word because here the probability score is high, right? So the third word has a higher probability and it is more related or it is conveying some meaning to the first word, right? So with the help of this softmax function, we can find whether a particular word is going to convey some meaning to that word under our study. So this entire process, what we do is we are trying to put it as an equation format. So attention of Q, K and V. Q is query, E and value is nothing but what? First we do Q into K transpose. That is this dot product. Q into K transpose. Then we scale it by root of dk. That is this term. Root of dk. Then we apply the softmax value. Then we apply the softmax function. After getting the softmax function, we multiply the softmax function with the value parameter, right? So this entire process is represented in terms of an equation form. So this gives the attention mechanism. Attention mechanism, how one word is related to another word that we can able to find. So now we have seen for individual words, right? So each word I have represented it as a vector. X1 is one vector, X2 is another vector. To make it much more faster, what I can do is I can make it as a matrix. Instead of having it as a vector, what I can do, I can make it as a matrix. So here I can have something like two rows. First row is for X1, second row is for X2. Then it becomes a matrix, right? So if I have 10 words, then first row is for first word, second row is for second word. So like that it goes on till the 10th word. Okay, 10th word, I will have X10. So this is a matrix. So the matrix computation can be really faster. So that is what we are going to do next. So here I take the two words. We define a matrix called as X, where in this X, the first row is your X1, second row is your X2. So vector for your first word, vector for your second word. So what I can do, I can multiply this matrix X with W of Q to generate the query matrix. Same way, X can be multiplied with W of K to generate the key value. X can be multiplied with the W of V to generate the value matrix. Right? So earlier I talked about array multiplication. Now I'm talking about matrix multiplication. That is the difference. After that, what we do? We take this Q matrix, multiply it with K power transpose, Then we do the scaling factor, do the softmax activation function, and then multiply it with the value matrix to get our Z matrix. Now, what does this first row indicate? First row indicates the output from the self-attention layer. Output from the self-attention layer for the word 1, first word. Second row is the output from the self-attention layer for the second word, right? So collectively we call it as Z matrix. Now, we have used a technique to find how one word is related to another word, right? Now this relation can be really good or it can be bad also. Why it can be bad? Because whatever we define for this matrix WQ, WK and WV, we are assigning in a random fashion, right? So we are setting this value in a random fashion. So if this random assignment is wrong, in that case, my attention for each word. So this W word 1 can be given attention with some other word, which may not be providing a value to this word, right? Because we don't know how to fix this W, Q, WK, WV, we don't know. We are trying to do it in a random assignment. Since we are doing it in a random assignment, the whatever we try to get the attention might be right or it might be wrong, right? So in order to avoid that, what we can do is, instead of having a single attention block, I can go with multi-head attention blocks. That is what we are going to do next, right? So this process I talked right now. Okay, this is one attention block. We take X matrix, we find Q, K, V using multiplying this value. So this is one attention block. Same way what I can do, I can have another attention block. I can have one more attention block, attention 3. Like that, I can have multiple attention blocks I can have. We can put this attention blocks in parallel, right? So thereby, if this attention is not properly determining, but the next attention might be properly determining the relationship, right? If I have more and more attention blocks, then the chance of wrongly getting an attention to particular words can be minimized. So that is why we go with multi-head attention blocks, right? Instead of having only one attention block, we are going to have parallelly multi-attention blocks. So that is what we try to indicate here. So here it is given in terms of a diagram. I take a X matrix. With the help of a X matrix, in the first attention block, I generate the output Z0. With the second attention block, I generate the output Z1. Same way here, I have used some 8 attention blocks. So we get 8 different outputs from the encoder block. So as I said, in an encoder, what are the 2 blocks? I have one is self-attention, right? So self-attention only we have discussed so far, right? So here what I try to say here is, instead of having a single self-attention block, I'm going to have multiple attention blocks. So each attention block is going to generate this Z0, Z1, Z2, Z3 till Z7. Since I'm going to use 8 attention blocks, then this attention block output, it should go to your feed-forward neural network. That is the next block. So feed-forward neural network, you might be knowing, you will have a input layer neurons. Then you will have hidden layer neurons. Then you will have output layer neurons. So this is hidden layer, input layer, and output layer, right? So I need to give the inputs to this feed-forward neural network, right? But here I have multiple matrices. Z0 is one matrix, Z1 is another matrix, Z2 is another matrix. So, but my neural network can get only a one-dimension vector here. Okay, it can get only a one-dimension vector can be applied to this neural network, right? So what we do here, we try to do a concatenation of all these matrices. That is what we do next. We concatenate all these outputs. So Z0 is the output from the attention at 0. Z1 is the output from the attention at 1. So like that it goes on. Z7 is the output from the attention at 7. So we concatenate all this. So what happens here? What is the first row indicates? So the first row indicates the output for word 0, right? So this part is the output for word 0 using attention at 0 block. Next one is the output for word 0 using a attention at 1, right? So I'm trying to concatenate all these outputs for word 0 together. Same way, second row is for word 1. So again, after concatenating all these values, what we are going to do? We are going to multiply this concatenated matrix with again another matrix called as WO, which gives the weight values for this inputs. How important is word 0? How important is word 1? How important is word 2? That will be determined with the help of this weight matrix. Again, how to say word 0 is important? How to say word 1 is important? We don't know, right? Then what we do? We assign this W of 0 also in a random fashion. Initially we do random assignment because we don't know whether word 0 is important in understanding the sentence or word 1 is important in understanding the sentence. We don't know, right? So we put weight values for each word, right? And this weight values will be assigned in a random fashion. So when I multiply this Z with this weight value, I get a output Z. So this Z goes as an input to the subsequent layer encoder block. Right? So we define the input and this input is multiplied with the weight values to generate the subsequent layer output. So the same thing which is given in terms of an equation here, right? What we do, we take the output from each heads, concatenate it. After concatenation, what we do, we multiply it with a matrix. So thereby multi-head attention is achieved. So we will see the overall process. We take these words, convert it into a vector. Then we use the matrix for query, key, and value. Multiply this X with this matrix to get the query matrix, key matrix, and value matrix. Then you generate the Z0 as an output. Same way for subsequent layer encoders. So this is for bottom layer encoder. So next one is for the next layer encoder. So like that, we have 8 such encoders. So after generating this Z0 to Z7, we multiply it with the matrix W0 to generate this Z. When we do that, we can see that here one such attenuation, attention block shows. So this orange indicates one such attention, green indicates another such attention, right? So you can see that if it is an orange attention block, in that case, this it is referring to the animal. Same way, this it is also referring to the 2 tier. In case of a green, okay, another attention mechanism. Okay, we are using 8 different blocks, right? We are using 8 different attention blocks. One attention block says it is referring to animal and 2 tier. Another attention block says it is referring to the street. it is referring to the tired. Same way, each attention block will say that it is related to this word, right? On a whole, on an average, when we sum up all these attention blocks together, we will be able to get the proper attention mechanism. So that is the concept behind your transformers. So here, for example, if I use some 8 different attention blocks, so each color is for an attention block, right? You can say that this blue color, this hit refers to the street. Okay, here you can see a darker line. Same way for green, it says it is tired. So like that, each attention block says that it is referring to this word. It is referring to this word, right? On a whole, as a whole, when I use all these attention blocks together, the noise gets reduced and I can get much more accurate attention mechanism. So that is what we do in our transformer. Till this, any doubts?
Sir, if attention block is getting increased for various combination, what would be the computation, or will it give output for all the, or will it respond for any sort of input, sir?
See, if I increase the number of attention blocks, so one thing you have to remember here is in transformer, my input goes in a parallel way, right? So it is not sequential. As we saw in our convolution neural network, my input goes to a convolution layer, then it goes to a pooling layer, like that it gets passed on. Whereas in case of here, what happens? My input goes parallelly to the attention mechanism, right? So if you see the input, it goes to the attention at 0. It also goes to the attention at 1 same time, right? It is not a sequential. So the computation, whichever happens in this attention blocks, I can have 100 attention blocks or 200 attention blocks, right? So, but the computation time is going to be same because the inputs are given in parallel to this attention blocks. So thereby my computation time is going to be same, right? So that is the biggest advantage of using this attention block when compared to your CNN. Whereas in CNN, what happens? My input should propagate from one layer to the another layer. So the first layer should produce an output, then it will be given as an input to the second layer. So there the computation time will be high. Whereas when I use a transformer, when I use a multi-head attention block, my input goes in parallel. Since it goes in parallel, the computation time will be very fast. Clear, sir?
Sir,
Thank you, sir. But is it the system, do the computation system, do we have that should be parallel computation? Should it do parallel computation, sir?
No, here we are going to do some just matrix multiplication, right? So we are going to perform this matrix multiplication in a parallel way. Only thing is my input should go to the matrix computation in a parallel fashion.
one more question, sir.
Thank you, sir.
In the sentence which you took, there was 11 words, and for that you took this 8 attention blocks. If at all the sentence contains some 30 words, then the number of attention blocks will be the same 8, or it has to be increased.
But the number of attention blocks does not depend upon the sentence length, right? Sentence length can be anything, right? So this attention blocks, it is based upon you. The programmer should decide whether I should have 8 attention blocks or 100 attention blocks. That you should decide, right? So here in the base paper, in the first paper where they have discussed this transformer, they have used 8 attention blocks, right? So by using 8 attention blocks, they are able to get proper attention for each word. So that is what they are trying to suggest, right? It is not that we should always have a 8 attention block. You can also increase it. If your attention mechanism is poor, in that case, what you can do is you can increase the number of attention blocks. So it is nowhere related to the input sequence.
Okay, sir.
Any other queries?
Sir, it's not query, sir. So due to network issue, I missed that paper. Is it possible to share that paper in the group, sir?
Which paper, sir? So here, attention is all you need is the paper. That is the base paper. Somewhere I have given that detail. So here you can see Ashish Vaswani et al. Attention is all you need. It is the 2017 paper, right, which discuss about this transformer model. Right? So then this architecture became very popular because we are doing parallel computation. So thereby the speed of computation will be very high.
Thank you, sir. I have taken screenshots, sir.
Okay. Anyway, I will share this PPT also with you. You can make use of it.
Thank you, sir.
Okay, so till this clear. So what are all the steps? Let me summarize once again. We take a sentence, split that sentence into words, use some embedding to convert the words into a vector. So after converting it into a vector, what we do? We are going to find three matrices: query matrix, key matrix, value matrix. So for that, we use some matrix called as WQ, WK, WV to get the query. So this diagram you please remember. This diagram you please remember. So after computing Q, K and V, what we do? We take a dot product of Q and K, then do a scaling factor of root dk, where this dk stands for the dimension of a key matrix. So key matrix is 64 dimension, right? So key matrix is 64 dimension. So we take root of dk, which is 8. Okay, we are trying to do a scaling option. Right now, the mask we are not going to use in the encoder part. In the decoder part, we'll be using this mask, right? So right now, we will not use this mask. Then after the scaling, we do softmax activation function, then multiply that softmax output with the value parameter, right? So after multiplying it with the value parameter, what we do? We get the Z values. So this is for single attention block, right? Similar concept can be done for multiple attention blocks. In that case, you will get multiple outputs. So in order to give these outputs to a feed-forward neural network, what we do is we try to concatenate all these vectors, concatenate all these outputs together, then multiply it with the W of 0. Why we need to multiply this with the W of 0? We need to know in a sentence which word is important, which word is not important, which word is going to give a meaning. So that we need to find with the help of a weight factor. So we need to assign what is the weight for this word 0, word 1. Since we don't know, we do initial random assignment. And we try to get the attention mechanism. So the attention mechanism which we get might be right or it might be wrong. If it is wrong, what is the problem? Our random assignment is the problem, right? So in order to eliminate such aspect, what we do is we go with multi-head attention blocks. That is what we have discussed so far.
Sir,
Okay.
another doubt, sir. The effect of transformers on images, sir. Is
Yeah,
there
I will come to that, ma'am. Right now, I'm talking about the sentence. Once you have understood this, the vision transformer is very simple,
Okay.
right? So I will come to that.
Okay, sir.
So now, next important thing is we are going to put the position mechanism. As I said earlier, my inputs go in parallel. Okay, this JE go in parallel, same as SUS, student, everything goes in parallel to the transformer architecture. Right? Since all the input words are going in parallel, we should have some mechanism that which word is coming first in our sentence, which word is coming second in our sentence. So that positional information we are missing. So to have that positional information, we are going to do positional encoding, right? So instead of supplying the input directly, instead of supplying our input directly to the transformer, what we do is we are going to do positional encoding. We are going to do. So what is positional encoding? I'm going to take a vector, add this vector with our input. So thereby I'm going to get an input with position information. So this x2, x1. So once again, let me repeat it. So this is, I have a sentence here. So I do embedding here. After doing embedding, I'm getting this x1, x2, x3, right? So this x1, x2, x3, I need to give it to the transformer. If I give it directly, then position information is missing because all the words are going to be executed in parallel, right? So to have the position information, what I'm going to do, I'm going to take a vector, right? I will say how we are going to get this vector, right? We are going to get a position vector T1, T2, T3, and I'm going to add this with the original input to get the input with the position information. So this input is with position information. So this input with position information is the one which is going to go into your encoder, not this original embedded vector, right? So whatever I'm going to give to the encoder is nothing but the input with position information I'm going to give. So thereby I know that which word comes first, which word comes second, which word comes last. That position I can able to determine. Now how to generate this positional encoding? So that is the next thing which we need to know. How to generate this T1, T2, T3. So there are two different mechanisms. One is these positions can be defined manually. So this JE is the first position. SUS is the second position. UDENT is the third position. Like that we can define. Depending upon where my word comes in a sentence, I can define the position. So that is one way, right? Second way is I can do this position encoding in a random fashion, right? I can put it in a random fashion. Third way is by using this equation, we can generate the position. So this equation is nothing but sinusoidal position encoding mechanism. So this is a simple formula where sine of position of the word divided by 10,000 power 2i by d, where d is the dimension of the embedding. Okay, how many dimension embedding, whether it is a 10 dimension vector or 20 dimension vector. Okay, so depending upon that, we generate the sine term as well as a cos term. So this is called as a sinusoidal position encoding. So when we look at it in terms of our numbers, for example, here I take some x1, x2, x3. You can see that initially it is 0, then it goes to 1. Right? So first two elements is 0, next two elements is 1. So this is one such encoding. If you see, look at this second encoding, 0.84. Let us take 0.84 is somewhere here. Then it goes to 0.01. Then it goes to 0.54. Then it comes to 1. Right? So this is 1.54. And here I have 1. So this is something like a sine wave. Okay, so if I can go like this. Right? So I am trying to define the position. So this is going to be at 0.84, then 0.01, then 0.54, then 1. So like that, if I have a multiple dimension increase, I can increase and decrease like this. Same way, I can have another position encoding like this, 0.91. It goes to 0.2. This is 0.91. So it goes to 0.0002. Then still it goes on to minus 0.42. Then it goes to 1. Then afterwards again it can come back. right? So it can go. So it again, it can be something like a sine wave I can generate. So like this, the position information can be embedded into the inputs. So such type of encoding is called as sinusoidal position encoding. And this is very popular encoding and it gives very good results. So when you look at it in terms of a graph, so for example, if I take 20 words, okay, so 20 words I'm going to take. So this each row is a word, right? So each row is a word, 0, 1, 2, 3. So like that it goes on till 90, right? So what we do, we take for each word, I have a 512 dimension input. Okay, 512 dimension input. So what we do, the position initial part, it will be generated using a sine function. Later part will be generated using a cos function. We have two equations, right? One is sine equation, another one is cos equation. So out of this 512 dimension vector, right? Initial part will be generated by a sine function. Later part will be generated by a cos function. So this is a position vector, right? It's position vector. So this position vector, I will add it with what? My input x1. Same way second row. Second row is another position vector. This is another position vector. Let me put it as P2. So this I will add it with x2. Same way for each word, I can do this, right? So P1 plus x1, I will get what? I will get x1. So here input plus position vector, I'm getting x1. So this x1 will go to the transformer as an input. So we are trying to put the positional encoding into the system. So now let us combine everything. So I take the words, do embedding, to convert it into a vector, then use positional encoding to add the position information. Then it goes into the self-attention block. In the self-attention block, we generate the output. Then what we do is one more important factor. What we do is this input gets added to the output of your self-attention block. This is called as residue adding, right? So residue gets added because as I start finding the attention between the words, there is a chance that I might lose some information. So I want to preserve that information. In order to preserve that information, my original information also gets added with the self-attention data. Right? So we try to add the original information. This is the original information. It is coming directly from here. So this original information gets added with the self-attention output. And we do normalize. And then the normalized data, it goes to the feed-forward network. Again, what we do, we preserve the information by adding it here. Again, I do normalization. So like this, we are going to do it for all the encoder blocks. This is encoder, bottom encoder. For top encoder, here we will have, instead of this, what we will have? We will have the output of encoder 1. Output of encoder 1 will be given as an input to this encoder 2. So like that it goes on. So this is the complete diagram. Input, positional information, then it goes to the self-attention block. It generates the Z1. Then the residue comes. It gets added and gets normalized. Then it goes to the feed-forward network. Then it generates an output. Now let us combine both the encoder and a decoder. Okay, so this, so far we have discussed about this block, encoder part, right? So from our input, it goes to encoder 1, encoder 1 output goes to encoder 2. So now this encoder output is generated, right? So this encoder output is given as an input to your decoder block, right? So decoder is what? As I said, again, I'm going to have a self attention, and then I'm going to have a feed forward network. In between what I'm going to have a encoder decoder attention block. What is this encoder decoder attention block? This information from the encoder comes to this encoder decoder attention block, right? So this is the extra layer. From where I'm getting this information? Encoder output, top encoder output comes to this encoder decoder attention block. So why this is required? Based upon the encoding, now my decoder, what it is going to do? It is going to generate a statement. It is going to generate a statement. I am a student. It is going to generate it, right? So in order to generate this statement, it is going to make use of the encoded information. Whatever encoded information is there, whatever attention data is there, based upon that, it is going to generate the data, sentence, right? So that is what happens in your decoder block. So it is same as that of your encoder. Only difference is we are going to have this encoder decoder attention. So when I talk about encoder decoder attention, what I'm going to get here is I'm going to get the K value and V value from the encoder block. K matrix and V matrix from the encoder block. And the Q matrix will be generated here in the decoder block. We require three matrices, right? Q, K, and V, right? Here what we do in encoder, we generate all the three matrices. Q matrix also we generate, K also we generate, V also we generate. Whereas in decoder, what we do, from encoder block, I get the K value and V value. Only Q is generated in your decoder block. Other process and all, it is same, right? So whatever the key values which we obtain from the encoder block is used for generating the new sequence. So this is how machine translation takes place. If I give a sentence in one language, it gets converted into a sentence in another language, right? So this is related to your natural language processing. Now let me talk about the vision transformer. Right? Now what we are going to do, using vision transformer, we are going to do the classification part. So here, instead of a text, I'm going to have an image patches. So here I have taken an image, divide that image into patches, right? So we have taken 9 patches. So each patch, I can convert it into a vector. Okay, this is vector 1, vector 2, like that we can convert it into a vectors. Then for each vector, we are going to put the position information. Which vector is first vector? Which vector is second vector? Which vector is, this is called as positional encoding. Okay, we do positional encoding. Then it goes into the transformer architecture, right? So now you can understand this diagram better. So my embedded patches goes to the multi-head attention block. So in multi-head attention block, I have multiple heads. One head will say that my information is available in the second patch. Another attention block might say that it is available in the 5th patch. Another attention block might say that it is available in this 3rd patch, right? So on a summary, if I have multiple heads, on an average, I can get some patches where I have the attention involved, right? So based upon that data, wherever I have the attention, it is given as an input to your neural network, right? And the neural network will make a prediction output. So this is how the image classification gets carried out. So in a vision transformer, there is no decoder, right? For machine translation, we require what? We require an encoder and a decoder, right? So I give input to this encoder. Encoder output goes as an input to the decoder. Decoder will generate the output. This is for machine translation. Right? So if I want to do classification, what we are going to do? We are going to do only the encoding part, right? So I take the input. Input goes to your encoder. Encoder gives the attention mechanism. So it goes into the neural network. Neural network makes the prediction. Right? So this is your vision transformer. If I want to generate an image, let us assume I want to generate an image. In that case, what we will do? Any idea from the participant side? If I want to generate an image, what we should do?
Divide that image into a number of matrices, and then give the position for that one.
Okay. Then I want to
Reverse
generate an image.
Reverse
Generative-
operation, sir.
What?
Reverse operation.
Reverse
like
operation in the sense? what we do?
decoding the
Yeah,
distribution.
so we need to have a decoder part. So for example, we take a model. What does this model will do? So we give input to this model. So this is a transformer model. We give input to this model. So it finds the attention blocks, attention data. Right? So we give inputs, multiple inputs we need to give, and it will try to find the attention blocks. Right? Once this is done, I can take this encoder output. Right? So encoder output, I can give it to a decoder. What the decoder can do, based upon this attention mechanism, this decoder can generate a new image. Okay, it can generate a new image. Is possible. Right? So that is how the image can be generated. New image can be generated. Right? Can you able to get this point? Hello? So what I'm trying to say here is, when I use a encoder, give inputs, so give the data set to the encoder. So you will generate the attention data. Right? For each image, there will be some attention. Right? So that attention data can be generated. Once it is generated, what I can do? I can take this attention data. I can give it to a decoder. Now the decoder, what it is going to do? It is going to generate. When it generates, it will make use of this attention data because it already knows for an image, this is the place where it has to give attention. Right? So now based upon the knowledge it has, now the decoder, what it is going to do? It is going to generate the image. This is called as generative AI. Okay, this is called as generative AI. Any doubts? So with this, I will wind up the session. Hello? Okay, so if there are no queries, so thank you for your kind attention. We can meet tomorrow. Thank you.
Thank you very
Yeah.
much, sir.